My name is Darren Thomas, and I am the Director of Educational Research Techniques. And this is Easier, Practical Applications of Machine Learning Algorithms in R. And so we are now in Unit 1 still, where we're learning about new decision trees for classification, and we're now in Unit 3. We're going to do our model development. So why don't we go ahead and move over to RStudio and see what's going on. So if you can see right here in this window in the upper left-hand corner, you can see that I have my my code right here. And so what essentially we're going to do is as follows. We're going to set our seed first, that way that we get consistent results. And then in lines 4 and 5, we have our code here. So what we're doing, and I need to also clarify that if you've closed RStudio since you've last did anything, you will have to reload the different libraries that we used in session 1-2, which is at the top of the code. I've already done that, so I don't need to repeat that step. But this will not work unless you've already have the libraries running. So in line 4, we're using the train function. And what the train function is going to do is that it's going to take our training set and develop our actual, our actual decision tree. And so remember, we're trying to predict job classification based on age, wage, and educational level. And we're using, of course, the R-part algorithm in this particular example. So all I do is I highlight what I want and I press Control Enter, and it's running and thinking, and now it's done. So I can take a look at it by looking at line 6, pressing Control Enter, and I get the information as follows at the bottom. So if you're not familiar with what's happening with decision tree, this is probably going to be confusing, but let me see if I can walk you through it. So at the top is CART. That's just the name of an algorithm, if you will, that we're using here. It's an acronym for something. And you can see that our sample size is 2,101. We have 3 predictor variables, age, wage, and education. That's just not familiar. And 2 classes for our dependent categorical variable, industrial information. And so then it talks about some bootstrapping that's happening here. And so what's happening is that the model is not taking all of the data at once. It's taking a piece of the data, making the model on that, and then taking another piece, and then it's trying to average them. And also what's happening here at the bottom is you have the CP. CP is what we call in data science machine learning, it's called a hyperparameter. It is a parameter that you as the researcher must set yourself in order for the model to run properly. And so the only way often that you can know what to set it to is to just take several different values at once. Now the beauty of the train function, which comes from the caret package, is that it does this at least partially for you automatically. So you can see we have 3 different values of CP. By the way, CP stands for complexity parameter. It is one of the hyperparameters associated with decision trees. And so it set 3 different values here. It picks them. And next to that, you have the accuracy of the actual model, which for us was 62%, 59, 55. And then we have the kappa right here. The kappa is like, it takes into account chance when trying to consider the accuracy. So you can see our kappa is not that great either. So overall, the best model has a complexity parameter of 0.004 with an accuracy of 62.25%. That's basically what this is telling us. And this information is found right here in this row right here. And even at the bottom, you can see the model, the computer tells you, accuracy was used to select the optimal model using the largest value. The final value used for this model was CP 0.004. So again, we're talking about complexity parameter here. And like I said, this is about how complicated the tree is, the decision tree, if you will. So that's kind of what's happening in the output. Now, this next part in line 7 gives us a nice, beautiful printout of what we have here. So you can see that it's off here to our lower right-hand corner. We have the actual model. But I'm going to do some things here and try to make this a little bit clearer for you. So here we have what we call the actual chart output, and they make a nice beautiful picture for us that makes it easy to follow what is happening. And so I'm going to try to explain it to you as best I can. So at the top you kind of have the parent node. We've talked about this before, the parent node. And so you can see that every node has a name. So industrial here, industrial again, information. How that name is determined is based on what is the majority in that node. So to make this as clear and as simple as possible, This first node is called industrial because if you look really close, 51% is classified as industrial, 49% is classified as information. Since industrial is the majority, that is why this node is called industrial. Now, underneath that, it tells you how much of the data is inside that node. So since this is the parent node, naturally 100% of the data is going to be there. So that's what's happening there. Now, what's happening at our next level right here is that I guess you can call it a branch if you will, we're having our first split. And our first split is based on education, whether somebody has an advanced degree or not. And the choices are either yes, they have an advanced degree, or no, they do not have an advanced degree. I'm sorry, advanced degree is greater than 0.5. All right, that's what's happening there. So advanced degree is where our node is split at. So if it's less than, it's yes. Over here, if it's greater than, that means no. It's over here. So what's happening is this. It sounds kind of weird, but what's happening is this. When people have an advanced degree, in other words, less than 0.5, no, it's not less than 0.5. It means greater than. So it's kind of like they're saying yes and no, but it should be no and yes. It's just backwards. But the yes is always to the left, and the no is always to the right. That's what's happening. So I hope that doesn't confuse you. So if people have an advanced degree, they go to our right. If they do not have an advanced degree, they go to our left, like that. That is what's happening there. Now, when we have this first split, notice what's happening here in the next node. So here it's still called industrial because 56% of the data is industrial. That's what's happening right there at this particular, this is a child node. And so over here, this is called information because now the majority is, their job is classified as information. And now here's something else that's very important. If you take 86, which is the percentage of data that's here, and 14, which is the percentage of data down here, it'll add up to 100. That's what's happening. And that's what's happening every single time when we split. And so right now we went from having 100% of the data in this parent node to 86% of it here and 14% of it here. Now, there's something else I need to explain. You can see that even after we make the division by advanced degree, our data is not pure. In other words, this is not 100% industrial, it's still 56-44. However, if you look closely, now you really got to pay attention here, you can see that there's a greater separation. So originally it was 51-49, but here we made an improvement, it's 56-44. It's still pure, even though it's not completely pure. And then over here, down for the information node, you can see that it went from 51-49 to 77-23. In other words, this is getting very pure over here, although we still have some misclassification. In other words, what's happening is that people who do not have advanced degrees are still having jobs where they're classified in the information zone. That's what's happening. People still have information type jobs without the advanced degree. Now, we're going to go back over here and we're going to see where the second split is at. Now we're looking at college grad. That's where the next split is at. And so now, if you look off to the left, if people are not college grads, here is the split, 63-37. It's still industrial, and we have 63% of the data here. For information, it's 38-62. That's why it's called information, and we have 23% of the data. Now watch this, 63 plus 23, so 63 plus 23, and we go right back to our 86%. So 63 plus 23, and oh, look over here, plus 14, look at that 14, plus 14, and now we go back to our original value of 100%. And so what's happening is that it's breaking down the groups based on whatever criteria is most efficient as determined by accuracy and the complexity parameter. And so that's what's happening. And again, notice also, at this node, the split was 56-44. When we split it, notice how it's more pure. Now it's 63-37. In other words, there's more separation between the groups, if you will. And also over here is 38-62. Again, not pure, but purer. That's what's happening. Now, maybe you're wondering, well, hey, Darren, didn't we have age in here? And didn't we also have a wage as well as variables? Yes, we did. But the model found that those particular variables were not relevant for making the groups purer. This is why they're not in the model. That's why they're missing. And so this is what we have here. So we have parent node, we have a child, but this child is a parent of these nodes, and we have the overall model here. So let's go back to RStudio now and see if we can wrap this up. Now, what we're going to do now is we're going to, in line 8, we're going to predict. Using the predict function, we're going to try to figure out how accurate our model is. Now, we already know the accuracy right here at 62.25, but just for the sake of practice, we're going to do this. Now, so I press Control Enter, and it's already done, and then I look at the table. So here's what we have here, if you look closely. So in other words, out of the 2,101, 829 were were classified as industrial and predicted as industrial. And then over here in the lower right-hand corner, 528 were classified as information and predicted as information. And then of course you have the misclassification. So they're classified as industrial, but they are predicted as information, classified as information, but labeled as industrial. So you can see that we have some problems here with these off diagonals here. This is where we're having our error at. And this is why our accuracy, is so low. So I just took the diagonals and divided them by 2,101, and you can see we got an accuracy of 64.5. That's slightly different from what the model says. I believe the model says 62, but you get the idea. Because this was using a slightly different algorithm, so you get a slightly different number, but not anything that's a major difference. So what we did in this video is as follows. We trained our model, we called it tree model, we used a function called train. Once we did that, we displayed the results, and that was right here, based on the highest accuracy as the CP, the complexity parameter, was adjusted. Again, the complexity parameter is just a hyperparameter for how complicated you want your model to be. If your model is too complicated, you can have issues with overfitting. Then we, after we did that, we used in line 7, we used a fancy RPOT plot to make this beautiful plot over here, which is a great visual of what we did and very easy for anybody to understand. And then I explained kind of the characteristics of the RPOT plot, in another piece of software. And then lastly, we predicted some data using the predict function in line 8. Of course, we had to make an object called train model, and then you made the table using the table function, where we compared the results of the trained model to the training set classifications. In other words, this part right here, training set $class, this is like the ground truth. This is like, okay, this is the answer. And we compared it to what our model predicted. And we got an overall accuracy of about 64%, which, depending on what your goals are, may be good or bad. It's not clear yet. So I hope that this was useful for you, and I look forward to seeing you in the next video. So take care.